Let's get into the documentation. More control flow tools. As well as the while statement just introduced, Python uses a few more that we will encounter in this chapter. If statements. Perhaps the most well-known statement type is the if statement. For example, here we've got the variable x set to the value of the integer returned from whatever is input by the user in response to the string please enter an integer. Here in this example, the user typed in 42, pressed enter, thereby updating the value of x to equal 42. After this, the if statement begins if x is less than 0, which it isn't. Update the value of x to 0 and print negative changed to 0. Else if x equals exactly 0, that is, remember, two equal signs is checking if it equals that, and it's not updating the value. Like this, it's actually changing the value of x to 0. This is asking if x is already equal to 0. If so, print 0. Else if x is equal to 1, then print single, and else, in any other case, print more. There can be 0 or more elif parts, and the else part is optional. The keyword elif is short for else if, and is useful to avoid excessive indentation. An if, elif sequence is a substitute for the switch or case statements found in other languages. If you're comparing the same value to several constants, or checking for specific types or attributes, you may also find the match statement useful. For more details, see match statements. For statements. The for statement in Python differs a bit from what you may be used to in C or Pascal. I'm not used to either of those. Rather than always iterating over an arithmetic progression of numbers, like in Pascal, or giving the user the ability to define both the iteration step and halting condition, as C, Python's for statement iterates over the items of any sequence, a list or a string, in the order that they appear in the sequence. For example, and it says no pun intended, like that's true at all, measure some strings here. Words. The variable words is set equal to this list containing 3 strings, cat, comma, window, comma, defenestrate. For w in words, remember this w can be anything. For gem in words, for word in words, it's just for every iterable item, or every item that can be iterated through in this list. Print that item and the result of calling the length function on it. So you would print out cat and then 3, because that's how many characters, that's its length, window 6, and defenestrate 12, if you called this function. Code that modifies a collection while iterating over that same collection can be tricky to get right. Instead, it is usually more straightforward to loop over a copy of the collection or to create a new collection. For instance, there's a sample collection here, this dictionary titled users. We know it's a dictionary because the curly braces, and we've got these key value pairs. Key separated from the value by a colon. It's got 3 items in this list, or this dictionary. So one strategy, iterate over a copy. So for user status, for key, comma, value, in users with the copy and items methods called onto it. If status is equal to inactive, then delete the thing in the users, in the dictionary titled users, at spot user. Or strategy, create a new collection. Active underscore users is now our empty dictionary that we've made just for this purpose. And you can always make empty dictionaries, empty lists, whatever, just by setting a variable equal to the brackets or the braces with nothing inside them. Now for user, comma, status, in users dot items, if status equals active, active users at user equals status is updated to the value of status. The range function. If you do need to iterate over a sequence of numbers, the built-in function range comes in handy. It generates arithmetic progressions. For I in range 5, for instance, print I would output 0, 1, 2, 3, 4, because it's 0 indexed, so range 5 means everything up to but not including 5, and the default starting point being 0. For I in range 5, print I, which outputs 0 to 4. The given endpoint is never part of the generated sequence. Range 10 generates 10 values, the legal indices for items of a sequence of length 10. So it is possible to let the range start at another number or to specify a different increment, even negative. Sometimes this is called the step. So here we've got the range function. We're calling the list function on the output of the range function, which has been given 2 arguments, which will define both a starting point and an end point if there's 2 arguments. And remember, the starting point is always inclusive and included in the list, the output, and the end point is not included in the list. Right? Now calling the list function on the range, on the output of the range function with these 3 arguments, you will have a starting point, an end point, and an increment at which it will step through that range. So with an increment of 3, that's going to go 0, 3, 6, 9. And same here, but with negatives. You got it. To iterate over the indices of a sequence, you can combine range and len as follows. So say we set the variable a equal to the value of a list containing the strings Mary, had, a, little, lamb. For I in range, the length of a, print I, a at I index. If you're confused by the way that I just phrased that, that's my fault, sorry. But you'll get it. Which would produce 0, it'll print first, here's the index at the point it's iterating through, and then the thing at that index, the way that this is set up. So it'll produce 0, Mary, 1, had, 2, 3, little, 4, lamb. Which is actually how computers sing that nursery rhyme. In most such cases, however, it is convenient to use the enumerate function. See looping techniques. A strange thing happens if you just print a range. Don't hear it on our full Mary. So, range, if you just type into the interpreter anyway, to the primary prompt, range 10, and hit enter, then this is what you'll get. What in the hell? In many ways, the object returned by range behaves as if it is a list, but in fact it is not. It's a listent. It is an object which returns the successive items of a desired sequence when you iterate over it, but it doesn't really make the list, thus saving space. We say such an object is iterable, that is, suitable as a target for functions and constructs that expect something from which they can obtain successive items until the supply is exhausted. Something you can iterate through. If you're not familiar with that word, you should look it up, because that word it's self-evident if you're familiar with the word iteration. We have seen that the for statement is such a construct, while an example of a function that takes an iterable is sum. So, for instance, we've got the range function with 4 passed into it, and then we're passing the output of that in as an argument to the sum function. And that is equivalent to saying 0 plus 1 plus 2 plus 3. It is every index that range 4 will iterate over is an added 1 by 1 together to produce the sum 6. Later, we will see more functions that return iterables and take iterables as arguments. In chapter data structures, we will discuss in more detail about list. Break and continue statements, and else clauses on loops. The break statement breaks out of the innermost enclosing for or while loop. A for or while loop can include an else clause. Not required. In a for loop, the else clause is executed after the loop reaches its final iteration. In a while loop, it's executed after the loop's condition becomes false. But I feel like that's self-evident if you work with them a little bit more. In either kind of loop, the else clause is not executed if the loop was terminated by a break. This is exemplified in the following for loop, which searches for prime numbers. So we've got this for loop for in range. And remember, this is just like the W in words earlier. Never forget, it can be confusing when it's new, but you could just call this Jimmy Jam if you wanted to. For Jimmy Jam in range 2, 10. For X in range 2, in. Here we've got another for loop nested inside this one. Keep track. If in modulo X results in 0, is no remainder, meaning it would be even, right? Print in, the string equals, the variable X, the string asterisk, and then the output of in floor divided by X. Then after you print that, break out of this the innermost loop that you're part of. Or else, if the loop fell through without finding a factor, print in, and the string is a prime number. Just a quick note about the indentation, keeping things together. Notice how this for and this else are aligned vertically. And so that means, they are both under this for loop. This is not a part of this for loop. It is, along with its vertically aligned brother here, part of the same family underneath this for loop. And so this function, if you gave it, or this loop, if you're passing in 2 and 10, will produce this output. Yes, this is the correct code. Look closely. The else clause belongs to the for loop, not the if statement. I don't read these ahead of time, so sometimes they surprise me. And sometimes I'm unnecessarily redundant because I didn't do that. I should probably start. When used with a loop, the else clause has more in common with the else clause of a try statement than it does with that of if statements. A try statement's else clause runs when no exception occurs, and a loop's else clause runs when no break occurs. For more on the try statement and exceptions, see handling exceptions. The continue statement, I'm going to give you one guess what that does. Also borrowed from C, continues with the next iteration of the loop. Sometimes programming isn't always hard. Don't worry about it. For num in range 2, 10. So remember, starting and including 2 and ending before you hit 10. If num modulo 2 returns remainder of 0, print the string found an even number followed by the variable num. I say the variable, the locally defined. I think that's a locally defined variable. What is the specific word for that? It's the temporary placeholder that's part of this for loop. Somebody remind me and correct me in the comments, please. Continue. After printing this, you would continue. And then we got print found an odd number, num, as the alternative, right? So it would be an accurate reflection. The pass statement does nothing. It can be used when a statement is required syntactically, but the program requires no action. For example, while true, pass. This is just a busy wait for keyboard interrupt, Control-C. I'm not actually sure what the hell that's supposed to mean. This is commonly used for creating minimal classes. For instance, a class titled My Empty Class, nothing inside but the word pass. This allows you to have that class as a thing that exists, and you can, go back to it later, or update or change it, later on the code. It's now you've defined it, but at the moment it does absolutely nothing. Another place pass can be used is as a placeholder for a function or conditional body when you are working on new code, allowing you to keep thinking at a more abstract level. It's a very lofty use for the pass. The pass is silently ignored. Relatable. So here we've got the function init_log. Defining the function init_log, it takes one parameter, *args. And here the programmer, lost in dreams of purely abstract realms, it has just wanted to define this, but then forget about it, so they just put pass so that they could go back to their ivory tower. And match statement takes an expression and compares its value to successive patterns given as one or more case blocks. This is superficially similar to a switch statement in C, Java, or JavaScript, and many other languages. But it's more similar to pattern matching in languages like Rust or Haskell. Only the first pattern that matches gets executed, and it can also extract components, sequence elements, or object attributes from the value into variables. So the simplest form compares a subject value against one or more literals. So here we've got a function http_error. We've defined this function. It takes one parameter. It has one parameter, status. And so when you call this, you will pass in whatever number, the status number that you got, be it 400, 44, 410, or something else, and it will match it. It will see if it matches any of these cases defined here. Match status against case 400. If so, if it does match, then you can return bad request. If it's 404, then you return not found. 418, return I'm a teapot. And here's that wildcard variable again, the underscore. So if it is anything else, something's wrong with the internet is what will be returned. Note the last block. The variable name underscore acts as a wildcard and never fails to match. If no case matches, none of the branches is executed. None of the branches are executed. Whoever wrote the Python documentation, questionable intellect. That was a joke. They're smarter than me. You can combine several literals in a single pattern using pipe, the pipe character, which, if you're a regular person and therefore have never used that ever in your life, it is on the same key as the backslash, and you would read it aloud as or. So like case 401 or 403 or 404. In any of those cases, if it matches to any of them, return not allowed. So patterns can look like unpacking assignments and can be used to bind variables. And I don't think that the tutorial has talked about unpacking assignments yet, so it's weird that they would refer to it. Maybe I missed that? I mean, unpacking assignments is where you assign multiple values to multiple variables at once by listing out the variables on the left-hand side, separated by commas, and all values, at the respective values that you're updating them with on the right-hand side, also separated by commas. So you could say A, B, C equals 1, 2, 3, and then you got a great hook for a song, but also you have updated the value of variable A to 1, the variable B to 2, and the variable C to 3, all in one line of code. It's beautiful. Now, in this case, match point, which they've explained as an x, y tuple, so like a coordinate, point coordinates. In the case that the coordinates are 0, 0, you print origin. In the case that the coordinates are 0, y, then you would print an f string, which formats. See, this f here being placed in front of the string means that it will be formatted with and pass in whatever you give here. Whenever it prints it, it will replace the things inside curly brackets here with what you pass in here. So it wouldn't actually say y equals curly braces y. It would say y equals 6 or whatever you put in as y. That's an f string. In the case, and don't worry because they haven't talked about that yet, so they'll have to at some point go into more detail. Case x, 0, print the f string x equals x formatted in, etc., etc. And here's the wildcard. In case any of those, none of those things, then you would just give value error, not a point, because this covers all possible things. You've got an issue if it doesn't hit any of them. Now it says study that one carefully. Just pause the video, I guess. The first pattern has two literals and can be thought of as an extension of the literal pattern shown above. But the next two patterns combine a literal and a variable, and the variable binds a value from the subject, point. The fourth pattern captures two values, which makes it conceptually similar to the unpacking assignment, the tuple x, y being updated to the value of point, which has been defined as a tuple already. If you are using classes to structure your data, you can use the class name followed by an argument list resembling a constructor, but with the ability to capture attributes into variables. So we were defining class point, and we're initializing an instance of that class within it with the dunder, double underscore, method in it. And we're passing in self, refers back to itself, the object, and x, y. and self.x will be updated to equal x, and self.y will be updated to equal y. And then underneath all of that, we define the function where underscore is, which takes in point, and we match that point against these cases here. To capture attributes into variables. I'm going to have to remember what the distinction here exactly about attributes and capturing them into variables here. I mean, I understand vaguely that we're capturing these, right? But somebody please correct me and explain that one. That would be great. A little bit more detail. You can use positional parameters with some built-in classes that provide an ordering for their attributes. Exempli grazie, data classes. You can also define a specific position for attributes in patterns by setting the _match_args special attribute in your classes. If it is set to x, y as strings, the following patterns are all equivalent and all bind the y attribute to the var variable. Right. I feel like I understand this, but I'm not sure. I feel like I must be missing something because I'm not sure why it's being said in a way. A recommended way to read patterns is to look at them as an extended form of what you would put on the left of an assignment to understand which variables would be set to what. So only the standalone names, like var above, are assigned to by a match statement. Dotted names, like foo.bar, attribute names, the x equals and y equals above, or class names recognized by the secondary prompt next to them, like point above, are never assigned to. Now, patterns can be arbitrarily nested. For example, if we have a short list of points with the dunder match_args added, we could match it like this. We've got the class point, we've got the dunder match args equaling the tuple, but it takes a string x and string y. Initialize an instance, which takes in self and x and y. Update self.x to equal x, update self.y to equal y, and then matches points. We can add an if clause to a pattern known as a guard. If the guard is false, match goes on to try the next case block. Note that value capture happens before the guard is evaluated. So, we've got this if here, and being added to a match pattern, it's apparently known as a guard. Because if the guard is false, match will go on to try the next case block. And notice that value capture happens before the guard is evaluated. Okay, so like first, capturing. And then we're asking if x is equal to y, then we can print this f string. If not, we move on and say it's not on the diagonal. Several other key features of this statement. Like unpacking assignments, tuple and list patterns have exactly the same meaning and actually match arbitrary sequences. An important exception is that they don't match iterators or strings. Sequence patterns support extended unpacking, such as a list containing x, y, star rest, and the tuple. Wait a second. Can tuples? Shit. This is some kind of sequence or collection. But I thought, okay, this is a rough one, guys. Damn. For me, I mean, it's a rough video. Works similar to unpacking assignments. The name after star may also be underscore, that wildcard. So x, y, star underscore matches a sequence of at least two items without binding the remaining items. Mapping patterns. Got a dictionary here, two items. Bandwidth as the key and value, or b as the value of one of the items, latency as the key, and 1 as the value of the second. Now this captures the bandwidth and latency values from a dictionary. Unlike sequence patterns, extra keys are ignored, and unpacking like **rest is also supported, but **_ would be redundant, so it is not allowed. Subpatterns may be captured using the as keyword. For instance, here we've got a check-init case. We're asking if point x1, y1 and point x2, y2 as p2. We'll capture the second element of the input as p2, as long as the input is a sequence of 2 points. Most literals are compared by equality. However, the singletons, true, false, and none, are compared by identity. Patterns may use named constants. These must be dotted names to prevent them from being interpreted as capture variable. So from enum, import enum, class, color, enum, passed as argument, or parameter, right? Red equaling the string red, green equaling the string green, blue equaling the string blue. Color equals the result of calling the input function on this string, and making it an instance of the color class. Right? Color equals an object of the color class, which is the result of asking for input with this string. I'm trying to figure out a way to word that. Is that right? Match color against these cases. I'm gonna have to just go study this more and then just come back and explain it in a better way. But the main project is reading this out loud, so I'm just gonna power on through. Defining functions. We can create a function that writes the Fibonacci series to an arbitrary boundary. For instance, so here is a way that we could do it. We could call the function fib, which is not, I would say, the best thing to name it. And it takes a single argument. The doc string here that is meant to describe the function, remember, it's called the doc string. It takes, we define two variables, a comma b, set them equal to the values 0 and 1 simultaneously. This is what I was talking about a little bit earlier, right? So a equals 0 and b equals 1 now. And then we start a while loop that checks it is a less than 1, or is less than n. If a is less than n, then print a, and end equals an empty white space, which is just giving it a space in between each output. And then simultaneously update the values of a and b to equal b and a plus b respectively. And because you set it up like this, you couldn't do this one at a time without making a third variable, a temporary variable, to store a value in. Because if you changed a to the value of b, and then tried to change the value of b to equal a plus b, then you would be doubling it. Because by the time that you're updating the value of b, the value of a was already changed to equal b. So now a plus b will just be the same as b times 2, which is not what they're trying to do. You're trying to add the previous number, not just double this one, right? So, but if you write it like this, it'll swap out the values simultaneously. I hope that makes sense. And at the end of the function, it prints. And now to call the function with 2000, which will set sort of the range, or series up to n, then we'll get all of the numbers in the Fibonacci sequence up to, not including 2000. The keyword def introduces a function definition. I'm surprised we haven't talked about that before. It's come up in every example. It must be followed by the function name and the parenthesized list of formal parameters. Remember that. So parameters are what you define in the function, as those are the spots where you will pass in arguments when you call the function. They're both the things that go in the parenthetical statement that's attached to the function name, but it's a parameter when you're defining it. It's an argument when you're passing it in. The statements that form the body of the function start at the next line and must be indented. The first statement of the function body can optionally be a string literal. This string literal is the function's documentation string, or docstring. More about docstrings can be found in the section Documentation Strings. There are tools which use docstrings to automatically produce online or printed documentation, or to let the user interactively browse through code. So it's good practice to include docstrings in code that you write, so make a habit out of it. The execution of a function introduces a new symbol table used for the local variables of the function. More precisely, all variable assignments in a function store the value in the local symbol table, whereas variable references first look in the local symbol table, then in the local symbol tables of enclosing functions, then in the global symbol table, and finally in the table of built-in names. So they start from inside out, going successively broader overarching layers of symbol tables. Thus, global variables and variables of enclosing functions cannot be directly assigned a value within a function, unless for global variables named in a global statement, or for variables of enclosing functions named in a non-local statement, although they may be referenced. The actual parameters, arguments, see, even the official stuff will confuse it in a sense. Like, I mean, why just say arguments? Yeah, they're not exactly the same thing. They're not completely synonymous. But the actual parameters, arguments to a function call, are introduced in the local symbol table of the called function when it is called. Thus, arguments are passed using call by value, where the value is always an object reference, not the value of the object itself. When a function calls another function or calls itself recursively, a new local symbol table is created for that call. A function definition associates the function name with the function object in the current symbol table. The interpreter recognizes the object pointed to by that name as a user-defined function. Other names can also point to that same function object and can also be used to access the function. So, if here, like we've got the function that we made earlier, fib, defined. If somebody were to just type the name of the function itself into the interpreter and press enter, then what we get is just this little pointer telling us where it is in computer memory. I mean, these numbers and shit would be different on every computer. And if we update the value of a new variable f to equal fib, and then we call f and passing in 100 as an argument, then it will be exactly the same as calling fib with the argument of 100. It will then output the Fibonacci series up to but not including the number 100. Now, coming from other languages, I don't. You might object that fib is not a function but a procedure since it doesn't return a value. I don't know what that is. In fact, even functions without a return statement do return a value, albeit a rather boring one. Judgy. This value is called none. It's a built-in name. Writing the value none is normally suppressed by the interpreter if it would be the only value written. You can see it if you really want to using print. So, if we call the function fib with the argument 0, the function is not going to be able to give us anything back but none. But so the interpreter it will give us literally none, nothing. It won't even print the word none, unless we call the print function on the output of this function with this argument passed in. Since the function returns none, print function will actually display the whole word none. It is simple to write a function that returns a list of the numbers of the Fibonacci series instead of printing it. So, let's say we've got another function, fib2, that we're defining. It takes one argument. It has one parameter. So it takes one argument. Its docstring, as again indicated by the 3 quotation marks on either side, says return a list containing the Fibonacci series up to n. So we define a variable result, set that equal to an empty list, as indicated by square brackets. We simultaneously assign the values 0 and 1, respectively, to A and B, respectively, Then a while loop begins. If while A is less than n, then we call the append we use the append method, which will allow us to add to the end of whatever value we pass in as argument to the list result. So result.append a will add a to the end of the list result, which is currently an empty list as we start, but we'll just progressively have more shit in it. Then a and b value, these are simultaneously updated to equal a and a plus b, respectively, and the result is returned. So if we update the value of this variable f100 to equal the output of the function fib2 with the number 100 passed into it as an argument, then calling the variable f1 is going to be the same. It will produce the same output as if we just, did this, which would produce a list. This list has now had all of these added into it. It is a Fibonacci series up to, but not including 100. This example, as usual, demonstrates some new Python features. As usual, the return statement returns with a value from a function. Return without an expression argument returns none. Falling off the end of a function also returns none. I'm not sure what is meant by falling off the end of a function there. I'd love it. What? The statement result.append a calls a method of the list object result. A method is a function that belongs to an object and is named object.methodName. It's not literally named that. That's a format in which it's named. Just want to be clear. where obj is some object. This may be an expression, and method name is the name of a method that is defined by the object's type. Different types define different methods. Different strokes for different folks. Methods of different types may have the same name without causing ambiguity. It is possible to define your own object types and methods using classes, C classes. The method append shown in the example is defined for list objects. It adds a new element at the end of the list. In this example, it is equivalent to result equals result plus a, the a spot in a list. But it's clearly more efficient. I just need a little bit of my computer juice. It helps me wake up and understand computers. It's delicious. Computer juice. More on defining functions. It is also possible to define functions with a variable number of arguments. There are three forms which can be combined. Default argument values. The most useful form is to specify a default value for one or more arguments. This creates a function that can be called with fewer arguments than it is defined to allow. So here we're defining a function ask_OK. And when we're defining it, we're putting in three parameters: prompt, keyword argument, retries, which we have set to the default value of 4, and reminder, which we have set to the default value of please try again. And while true, reply equals the input function called on prompt if reply in this dictionary. If the reply that you get is anything that is in here, so the user types in Y or they type in YE for some reason and they're just thinking of Kanye, it's still going to be counted as if they answered yes. And this sort of thing is used all the time because people often fuck up. So you can't just be like, only if you answer no exactly will this work. You have to account for the fact that people will answer no in different ways. So if reply in this one, return false. Retries, we're setting this variable here, equals retries minus 1. After these have been gone through, this means that it will take the value assigned to retries, which by default equals 4, and it will remove 1. It will update the value to be itself minus 1. And if the value of retries is less than 0, meaning if you've run through this loop 4 times and therefore taken out all of, from the default value of 4, 1 by 1, taking it down to 0, then you get a value error. It will say invalid user response. And it will print reminder. Please try again. And so you notice that, like, so you're not passing in 1, 2, 3 arguments to when you call it. This function can be called in several ways. So giving only the mandatory argument, so like we're calling a function ask OK, and we're putting in the string do you really want to quit. Giving one of the optional arguments, such as OK to overwrite the file, comma 2, or even giving all arguments, OK to overwrite the file, comma 2, comma come on, only yes or no, dumbass. This example also introduces the in keyword. This tests whether or not a sequence contains a certain value. Or another way to put that is whether or not a certain value is in a sequence. Seems like a missed opportunity there. The default values are evaluated at the point of function definition in the defining scope. So that I equals 5, we've set this variable I equal to the value of 5. We're defining a function f, which takes 1 keyword argument, which by default equals I, print, and then prints that argument. If we then change the value of I to 6, and then call f with no arguments, it will print 5. So basically, since I is set to the value of 5, whenever this function is defined, and this parameter is set to a default value equaling I, it's going to set arg to the default value that whatever I is at the point, where it's defined. So even though we update I after we've defined this function, if we just call the function without argument, it will still produce 5, whatever this default value is set to at the time, if that makes sense. It's poorly worded, but important warning, the default value is evaluated only once. This makes a difference when the default is a mutable object, such as a list, dictionary, or instances of most classes. For example, the following function accumulates the arguments passed to it on subsequent calls. This function f, which takes in 2 arguments, a and an empty list set to L, and it takes that list and it appends to the end of that list whatever is passed into A, L.append A, and then it returns that list. If we call it multiple times with multiple different arguments passed in for this value of A, then it will keep on, it'll successively append each one to the list, and this list L, which is going to keep on getting bigger and bigger. And so print f1, print f2, and print f3 will result in a list that contains 1, a list that contains 1 and 2, and a list that contains 1, 2, and 3. Now, if you don't want the default to be shared between subsequent calls, you can write the function like this instead. Nobody's fucking stopping you. Define f, takes a, and it sets the value of L equal to none. And if L is none, then L becomes an empty list, and we append the value of A to the end of it, and then return it. And so, after the first call, it will never be none. So it'll never be set to an empty list. Wait a second, though. Wait, no. We're getting that backwards. It'll always start over, because that's set as the default value, right? Surely, that's what they're trying to say. Again, I'm really relying on that principle. What is it called? Where you can't, if you say something, the surest and fastest way to get a thorough answer to any question is to simply claim the opposite, claim something untrue online. So I'm going to be publicly making a lot of mistakes so that you people can correct me. Functions can also be called using keyword arguments of the form quarg equals value. For instance, the following function, parrot, which takes in voltage, the keyword argument state equaling the string a stiff by default, the action equaling voom by default, and type equaling Norwegian blue by default. See, Jesus Christ, it's the dorkiest shit. There's more Monty Python references if you're a kid. Like, I don't know if you do, but print, you would print this parent wouldn't, followed by whatever is passed into action, followed by end equaling the space. Then you'd print if you put, then you'd print whatever you pass in as voltage. Blah-da-dee-blah-blah-ba-dee-ba-da-blah, accepts one required argument, voltage, and 3 optional arguments, state, action, and type. This function can be called in any of the following ways. So you could call it with one positional argument, such as 1000. You could call it with one keyword argument, where it is actually voltage is set explicitly equal to 1000. You could call it with 2 keyword arguments, in which you've got both voltage and action, both set explicitly to an integer and to a string, respectively. You could do the reverse. You can do 3 positional arguments, in which you just pass in 3 different strings, a million, bereft of life, and jump. Or you can mix it up, get crunk, 1 positional, 1 keyword. But all of the following calls would be invalid. Calling it without the required argument, calling it with a non-keyword argument after a keyword argument. So note there's an order, arg, star arg, quarg, star quarg. If that doesn't make sense, that's okay. Duplicate value for the same argument, so you can't pass in a positional argument for voltage and then explicitly the keyword argument for voltage. And you can't pass in a keyword argument that isn't defined in the function definition, obviously. In a function call, keyword arguments must follow positional arguments. All the keyword arguments passed must match one of the arguments accepted by the function. E.g., actor is not a valid argument for the parrot function. And their order is not important. This also includes non-optional arguments, such as parrot, with voltage equaling 1000 passed in as the argument, is valid too. No argument may receive a value more than once. Here's an example that fails due to this restriction. So here we've got the function, a function titled function, confusingly, that takes in one argument a, and it has nothing in it but pass. If we call that function with a positional argument 0, and then explicitly the keyword argument for a as well, it'll be like, what the fuck are you trying to do? You're trying to put 2 chickens in the same box at once. When a final formal parameter of the form star name is present, it receives a dictionary. Well, that was my favorite gift when I was 12. Containing all keyword arguments except for those corresponding to a formal parameter. This may be combined with a formal parameter of the form star name, described in the next subsection, which receives a tuple containing the positional arguments beyond the formal parameter list. So star name must occur before star name. For example, it's like the hierarchy at a music festival. I'm star name. You're just fuck. Comedy hour. For example, if we define a function like this, define cheese shop, which takes in kind, takes in star arguments, and takes in star keywords, which will print the string do you have any, followed by what's passed into kind, followed by the string question mark. Then it will print the string I'm sorry we are all out of, followed by whatever is passed into kind. And then runs a for loop, and for arg in arguments, print arg. Print the string hyphen times 40, and for kw in keywords, print the keyword followed by the string colon, followed by keywords, whatever is at spot keyword in sequence keywords. So it could be called like this: cheese shop function with passed in the string Limburger, comma, the string it's very runny, sir, comma, the string it's really very, very runny, sir, comma, the specific keyword or keyword argument shopkeeper set to Michael Palin, keyword argument client set to John Cleese, and the keyword argument sketch set to cheese shop sketch. And keyword argument nerd set to you. And of course it would print, do you have any Limburger? I'm sorry, we're all out of Limburger. It's very runny, sir. It's really very, very runny, sir. Flawless accent. Shopkeeper, Michael Palin, client, John Cleese, sketch, cheese, shop, sketch. Note that the order in which the keyword arguments, and note, just in case you missed it, this line break here, remember, that was just hyphen times 40, because you can operate on strings like that. By default, arguments may be passed to a Python function either by position or explicitly by keyword. For readability and performance, it makes sense to restrict the way arguments can be passed, so that a developer need only look at the function definition to determine if items are passed by position or keyword, or by keyword. A function definition may look like this. The function f, it's got these positional-only arguments. We've got arguments that could be positional or keyword, and we've got keyword-only arguments, where / and star are optional. If used, these symbols indicate the kind of parameter by how the arguments may be passed into the function. Positional only, positional or keyword. Positional only is the default, right? Positional or keyword / keyword only with a star. Keyword parameters are also referred to as named parameters. Positional or keyword arguments. If / and star or asterisk are not present in the function definition, arguments may be passed to a function by position or by keyword. So positional-only parameters. Looking at this in a bit more detail, it is possible to mark certain parameters as positional only. If positional only, the parameter's order matters, and the parameters cannot be passed by keyword. Positional only parameters are placed before a /. / is used to logically separate the positional only parameters from the rest of the parameters. If there is no / in the function definition, there are no positional only parameters. Parameters following the / may be positional or keyword only. Keyword only arguments. To mark parameters as keyword only, indicating the parameters must be passed by keyword argument, place a star in the arguments list just before the first keyword only parameter. Function examples. Consider the following example function. Definitions by definitions by, oh my god, I feel like there's a by in there. Consider the following example function definitions, paying close attention to the markers / and star. You've got standard arg, the function, standard arg, it takes one arg and it prints arg. Got positional only arg, which takes an arg with a / after it in the when it's defining the parameters. Print arg. Got keyword only args with a star before it when defining the parameters. And we've got combined example, which takes piece of shit only, followed by /, followed by standard, followed by the star, followed by keyword only. And therefore, that's what it do. The first function definition, standard arg, the most familiar form, places no restrictions on the calling convention, and arguments may be passed by position or keyword, such as here where it's positional and here where it's keyword. Bada bing, bada boom. The second function, POS only arg, is restricted to only use positional parameters as there is a / in the function definition. Bing bong 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 bong, that's self-explanatory. The third function, keyword only args, only allows keyword arguments as indicated by the star in the function definition. So you try to give it a positional, it gives you a type error. You have to give it the keyword. And the last uses all three calling conventions in the same function definition. So we will get a type error if it is all positional, a type error if it's all keywords, and you won't if you do it right. Finally, consider this function definition, which has a potential collision between the positional argument name and star keywords, which has name as a key. This function is called foo, because that's a convention that's still going strong for some reason. And it takes in name and star keywords. And if it tries to return name in keywords, there's no possible call that will make it return true, as the keyword name will always bind to the first parameter. For example, say we tried to call that function passing in 1, then passing in star a dictionary with name as a key, 2 as the value. It will, by trying to find name in that, it's going to get multiple values for argument name. By using / positional only arguments, it is possible, since it allows name as a positional argument and the string name as a key in the keyword arguments. So say we said, in defining it, name, comma, / comma, star keywords, and we then had it return name and keywords. We could pass in positional 1 and star this dictionary with name as the key, and then it would return true. In other words, the names of positional only parameters can be used in star keywords without ambiguity. Alright, dig a dog. Recap. The use case will determine which parameters to use in the function definition. So, if we have this terrible function we are defining that's just called f, it takes pos1, pos2, / then pos or keyword, then a star, then keywords. Right? As guidance, use positional only if you want the name of the parameters to not be available to the user. This is useful when parameter names have no real meaning, if you want to enforce the order of the arguments when the function is called, or if you need to take some positional parameters and arbitrary keywords. We use keyword-only names when those names have meaning, and the function definition is more understandable by being explicit with names, or if you want to prevent users relying on the position of the argument being passed. Oh shit. Laptop almost died, which would have destroyed the whole recording. That would have been annoying. Okay. For an API, use positional only to prevent breaking API changes if the parameter's name is modified in the future. Arbitrary argument lists. Finally, the least frequently used option is to specify that a function can be called with an arbitrary number of arguments. These arguments will be wrapped up in a tuple, see tuples and sequences, before the variable number of arguments. 0 or more normal arguments may occur. So, say we define a function write multiple items, which takes in file, separator, and star args. File.write, the write method called, are attached to it, and then separator.join with args passed in. See, normally these variadic arguments will be last in the list of formal parameters because they scoop up all remaining input arguments that are passed to the function. Any formal parameters which occur after the star args parameter are keyword-only arguments, meaning that they can only be used as keywords rather than positional arguments. So, say we define a function concat that takes in star args and then separates it with / and it returns the result of calling a join method on sep with args passed in. So we call the function concat with the strings Earth, Mars, Venus. It'll return Earth/Mars/Venus. All three of those arguments separated by the forward slash. And if we wanted to do the same thing, but we pass in as keyword arguments sep and change that to period, it'll give us the same thing, but separated with a period. Unpacking argument lists. The reverse situation occurs when the arguments are already in a list or a tuple but need to be unpacked for a function call requiring separate positional arguments. For instance, the built-in range function expects separate start and stop arguments. If they are not available separately, write the function call with the star operator to unpack the arguments out of a list or tuple. So, say, here's an example of a normal call. Like we're turning into a list the output of calling the range function with the arguments 3 and 6. It'll give us the range from 3 to 6, 3 inclusive, 6 exclusive, right? So it'll make a list out of that 3, and it'll give us 3, 4, 5. Let's say we first defined a variable args as being a list with 2 items in it, 3 and 6. We can then use that list by unpacking it. We can use that as if it's 2 separate numbers, basically. We'll call the list function on the output of the range function with star args passed in as argument. Star args, meaning the unpacked list args. And that will be just like putting in 3, 6, because it unpacked a list consisting of the values 3, 6. And so we'd get the exact same output. In the same fashion, dictionaries can deliver keyword arguments with the star operator. So say we've got the function parrot defined. It takes in voltage, state, default value being a stiff, and action, the default value being voom. And then we tell, and part of its function definition is to print this parrot wouldn't, followed by whatever's passed into action, followed by an end marker being a space. Then to print if you put, followed by whatever's passed into voltage, followed by the string volts through it, followed by the ending with the space. And then print ease, followed by whatever's passed into state, followed by the string and exclamation point. And so if we then, after defining this function, we create a dictionary, D, that contains voltage as key and 4 million as value, state as key, bleeding demised as value, and action as key, and voom as value for 3 key value pairs. And then we call the parrot function with star D. It'll be the unpacked dictionary D. Will produce this parrot wouldn't, voom, if you put 4 million volts through it, is bleeding demise. I fucking have seen that, of course. I can't do the accents. It's been too long since I've seen any Monty Python. Lambda expressions are pretty fun. Half-life anybody. Small anonymous functions can be created with the lambda keyword. This function returns the sum of its 2 arguments, lambda a, b, a plus b. Think about this for a second. Lambda functions can be used wherever function objects are required. They are syntactically restricted to a single expression. Semantically, they are just syntactic sugar for a normal function definition. Like nested function definitions, lambda functions can reference variables from the containing scope. So, say we define a function titled make_incrementer, which takes an one argument. Right? Return, and it will return the lambda of x plus n. Then let's say we set a variable f equal to the result of calling a make incrementer function with 42 passed in as argument, because of course it has to be 42. Then if we say call f0 with 0 passed in, we'll still get 42. If we call f with 1 passed in, then we get 43, because it's x plus n to x. That's what's returned. So the above example uses a lambda expression to return a function. Another use is to pass a small function as an argument. So say we had this list of tuples that we title pairs. Remember, it's a list, square brackets, with these tuples, little pairs in parentheses. That's right, isn't it? The tuples are 1 comma and the string 1. It's the integer value followed by a string representing that integer value. Pairs dot sort with key equaling a set equal to lambda of pair at spot 1. If we call pairs, then we will get these. We basically get this sorted, right, by sorted by its values, right, I think, and not its keys. Yeah, right, yeah. So that it's sorting these now based on their values alphabetically. So now it returns 4 first, right? I think that's right, because it's calling 1, index 1, on these things, and so index 1 would be the second part. Hope that makes sense. I hope it's right. Here are some conventions about the content and formatting of documentation strings. Nobody's ever going to fucking watch these. The first line should always be a short, concise summary of the object's purpose. For brevity, it should not explicitly state the object's name or type, since these are available by other means, except if the name happens to be a verb describing the function's operation. This line should begin with a capital letter and end with a period. If there are more lines in the documentation string, the second line should be blank, visually separating the summary from the rest of the description. The following line should be one or more paragraphs describing the object's calling conventions, its side effects, etc. The Python parser does not strip indentation from multi-line string literals in Python. So tools that process documentation have to strip the indentation explicitly if desired. This is done using the following convention. The first non-blank line after the first line of the string determines the amount of indentation for the entire documentation string. We can't use the first line since it is generally adjacent to the string's open end quotes, so its indentation is not apparent in the string literal. A white space equivalent to this indentation is then stripped from the start of all lines of the string. Lines that are indented less should not occur, but if they occur, all their leading white space should be stripped. The equivalence of white space should be tested after expansion of tabs to 8 spaces normally. So here's an example of a multi-line doc string. We've got quotation marks, quotation mark, quotation mark, 3 of them. Do nothing but document it, then they pressed enter, then they pressed enter again. No, really, it doesn't do anything. Then they pressed enter once more, and then finally closed it out, and then pass. Now, if we call the print function on the my function with the doc dunder method, which accesses and reveals its doc string. Okay, right. Then it will print the doc string, and it will look like this. The first line is right up here. That second line is still, that empty line is still present. And then the third one, then you see the indentation. So don't do it like that, why would you? Function annotations are completely optional metadata information about the types used by user-defined functions. Annotations are stored in the __annotations __ attribute of the function as a dictionary and have no effect on any other part of the function. Parameter annotations are defined by a colon after the parameter name, followed by an expression evaluating to the value of the annotation. Return annotations are defined by a literal -chevron, followed by an expression between the parameter list and the colon, denoting the end of the defining definition statement. The following example has a required argument, an optional argument, and the return value annotated. So here, you know what? I just pause the video and take a look at that one. That's not really worth breaking down. verbally, intermezzo, coding style. So now that you are about to write longer, more complex pieces of Python, it's a good time to talk about coding style. So why don't you just take a seat, buddy? Most languages can be written or more concise, formatted in different styles. I mean, it's not more concise, it's a longer word. They mean more precisely, or more, some are more readable than others. Making it easy for others to read your code is always a good idea, and adopting a nice coding style helps tremendously for that. So for Python, PEP 8 has emerged as the style guide that most projects adhere to. It promotes a very readable and eye-pleasing coding style. Every Python developer should read it at some point. Here are the most important points extracted for you. Use 4-space indentation and no tabs. This frustrates me so much. 4 spaces are a good compromise between small indentation, allows greater nesting depth, and large indentation, easier to read. Tabs introduce confusion and are best left out. I don't know what that. I'm sure that there's some truth there. I'm not experienced enough to understand why. It seems the exact opposite to me. I mean, it's so much easier to mistake 3 spaces for 4 than it is to mistake no tab for tab. Like, and plus in the IDEs, like, it'll automatically tab for you, and like that's the default. So it just seems like you have to go out of my way to do 4 spaces. But I mean, I'm sure that they know what they're talking about more than I do. Wrap lines so that they don't exceed 79 characters. This helps users with small displays and makes it possible to have several code files side by side on larger displays. This I get. Use blank lines to separate functions and classes and larger blocks of code inside functions. Definitely. When possible, put comments on a line of their own. Use docstrings that explain what your function does. Use spaces around operators and after commas, but not directly inside bracketing constructs. So you would put a space after this comma here to clarify, but you don't want to put it, there's no need to put a space like after or before each parentheses. That just makes it needlessly big. Name your classes and functions consistently. The convention is to use upper camel case for classes and lower case with underscores for functions and methods. Always use self as the name for the first method argument. And don't use fancy encodings if your code is meant to be used in international environments. Python's default, UTF-8, or even plain ASCII work best in any case. Likewise, don't use non-ASCII characters in identifiers if there is only the slightest chance people speaking a different language will read or maintain the code. Bada bing, bada boom, good job, you did it.